Hi all, my name is Yash and I'm going to talk about the planted models for the densest k-Subgraph problem, and this is joint work with Anand Lewis. So let me just jump right in. So my talk is divided roughly into three parts. The first part is the introduction. The second part is the main crux, where I'll discuss about the densest k-Subgraph problem and our results and so on. And the third part is the conclusion. So introduction. So in this particular um, section, I'll discuss about the different models of computation, the different models which we consider in our paper. So the graph which we sort of work on is constructed in stages. So we start with the empty graph on n vertices, and this particular graph is now divided into two parts, one of size k, which we call as S, and one of size n minus k, which we call v minus S. So then we plant some important structures, something of interest onto S, and this some structure of interest which we sort of want to maybe recover. So I'll talk more about what is our goal and so on. So first, let me complete the model construction. So the subgraph S cross V minus S is a random graph. So this is a graph uh, in which each pair of S each pair of S cross V minus S is added independently with probability P. So an edge is added independently with probability P. And let's say for now V minus S is also a random graph with the same parameter P. So um, so this is the classical, the subgraph on V minus S is the classical Erdos-Renier random graph on n minus k vertices and parameter p. So think of k as some polynomial in n, say square root n or n raised to power 1 by 3 and so on, and p as something as 1 upon poly of n, can even be a constant, say 1 by 3 or 1 by 10 and so on. And the goal of our work is to sort of recover s. So say you plant something, some subgraph of interest onto S, and in a random graph, in a large random graph, and now you want to recover S. So before that, one more, there's another step to um, there's another step in our model construction. Let me say it, but I'll not tell much about it in detail. But for the sake of completeness, let's say the last step of our model construction is there is a monotone adversary which is allowed to delete any amount of edges outside the subgraph S. So any edges in S cross V minus S, and within V minus S, this monotone adversary is allowed to delete, and we want to now recover S. So for now we can ignore that uh, there's some such adversary, but it turns out handling it is not a big deal. But yeah, um, so this is sort of like the weakest model of computation, where you plant something of interest in a random graph and now you want to recover it. I'll tell you why I call this the weakest model, like, in a minute. A slightly harder problem, or the intermediate model, as I say, is when V minus is some special graph. So think of it as some special graph which maybe encapsulates the random graph. Like, it may or may not do it, but like, let's say for now it is some special graph, so it has some more structure. So some structure which we can use to maybe get information about S. So V minus S is some special graph. So this is what I call the intermediate model. Then one of the hardest models in this semi-random model regime is the Feige-Killian model. So named after these two theoretical computer scientists. The Feige-Killian model talks about when V minus S is an arbitrary graph. So here there is no randomness, or there is no special structure on V minus S, the only amount of randomness is between the s cross v minus s, and now you want to recover s. So the goal is always to recover s. Um, and the worst case model is when there is no randomness at all, and even the subgraph on s cross v minus s is a arbitrary graph. So recall that, like, so in this particular talk, we are going to study mainly the intermediate model, which is when v minus s is some special graph, or the weakest model in which v minus s is a random graph. So I'll only talk about these two particular models, and but note that in contrast to the typical approximation algorithms literature, where the goal is to get better algorithms as in the sense of better approximation factors, here our goal is not just that but to also recover s. So I'll say more about when I talk about the concrete problem. So if you're not understood anything till now, most of these things I'm going to repeat in the second part of my talk. So coming to the concrete problem which we study in our paper, it is called the densest k-subgraph problem. So let me start by defining the problem. So the input to this problem consists of a undirected and possibly a weighted graph and a parameter k, and you are supposed to output a subgraph on k vertices with the maximum average degree. So you are given a large graph, undirected and possibly weighted, and a parameter k. You are supposed to select k vertices with the maximum average degree. So let me set some notation here. So let's say for a subgraph t, delta of t denotes its average degree, and it is defined as you compute the sum of degree of u in t and sum this thing over all such vertices and divide by the size of t. So this is defined as the average degree of t. Just pictorially, um, if t is the subgraph, if t is the corresponding subgraph, then um, only the edges on green color will be accounting for the average degree of t, and none of the red edges will account for the average degree of subgraph t. So what is known about this particular problem, the densest k subgraph? So in the worst case, it is known that, I mean, it is clear that this particular problem is clearly a NP-hard problem because it is a generalization of the popular the clique problem. So we cannot expect to find a exact algorithm in polynomial time for this particular problem. On the algorithmic front, it is known from the work of Bhaskara et al. That you can approximate this problem in the time n raised to power O of 1 upon epsilon to a factor of n raised to power 1 by 4 plus epsilon. So this is currently the best approximation factor known for this problem, and um, uh, this is due to the work of Aditya Bhaskara et al. Coming to the hardness side, it was shown that Court had showed that it does not have a p-task unless NPS sub exponential algorithms, and recently Manurangsi had showed that assuming the exponential time hypothesis, there is no polytime algorithm that approximates this problem to within a factor of n raised to power 1 upon log n to power c, where c is some universal constant. So if you look at the second and the fourth point, there is a huge gap between the hardness and the best known algorithm. So it is natural to study this particular problem in some easier instances, in some instances where we can develop some nice algorithms and possibly um, get away with this hardness. So the two semi-random models which we consider in our paper as follows. So these are of the intermediate model where S is some dense subgraph of size k and average degree d. S cross V minus S is a random graph. Each of the pairs of S cross V minus S it is added with independently with probability p, and V minus S is a expander graph. So it is not a random graph, but it is a n minus k d prime comma lambda expander. So what do I mean by this? So recall that this is in the intermediate model because V minus S is some special graph. It's not arbitrary, it's not random, but it's some special graph. So an expander is n minus k d prime lambda expander is one in which is supported on n minus k vertices. It is d prime regular, and lambda is this defined as based on the eigenvalues of the adjacency matrix of this subgraph, and it is the maximum of the modulus of lambda 2 and the modulo of lambda n minus k. And so qualitatively you can think of it as a sparse graph. It is a sparse well connected graph, but it is essentially a sparse graph. And coming to the second semi-random model, it is constructed in a special way. So this also falls in the intermediate category, where if you take any subgraph in V minus S, which is shown by this green colored boundary, uh, if you take the average degree of this particular subgraph, it is slightly smaller than D. So recall that D was the average degree of S, and this particular fact is true for all such subsets of V minus S. So I'll repeat. So you take any particular subgraph within V minus S, its average degree is less than T. It is less than gamma D. You can just think of it as slightly smaller than D, where D was the average degree of the planted dense set on planted dense set of size k on uh, an average degree d. So what are our results? So our results actually depend on the structure S, the planted set S. So in case the S has some average degree d, we give an algorithm which outputs a subgraph on k vertices and average degree slightly smaller than d. When S is d regular, when S is more structure, then we can show that we do not just output a subgraph of size k and average degree slightly smaller than d, but this particular subgraph has a large overlap in the large overlap of vertices with S also. So we can show that as well. When S is a clique, when let's say S is a clique, then we can show that we can recover S completely. So I'll not talk more about these two particular models now, but this is sort of our results. We for the sake of this presentation, I'm going to come back to the easier model. This is the case when S is some dense subgraph of size k and average degree d. S cross V minus S is random as always, and V minus S is a Gn minus Kp graph. So when V minus is a random graph, I'll just talk more about this particular case. So you can restate this particular problem. So what was our problem? The problem is to recover S. So uh, we can sort of restate this problem in terms of this, that what is the smallest value of d in terms of kp and n for which s can be recovered. So this is sort of our problem, and uh, the reason for choosing, like the reason for having a lower bound on d is the following. The smaller the value of d, the problem gets harder, right? Because when as d increases, s the it will like stand out more, and so it should be at least qualitatively easier for us to detect s. So that's why, like, the smaller the value of s, the smaller the value of d at which you can solve this problem, the better your algorithm is. This is a generalization of the planted clique problem, and like both this particular problem and the planted clique problem has been studied in the literature. And there are, so this paper by Aditya Bhaskara gives a threshold of d equal to omega of np to the log k base n, and our threshold is maximum of pk comma square root np. So for the sake of comparison, consider different ranges of k, and recall that the smaller the value of the threshold, the better our algorithm is. So from this chart, one can see that in certain ranges of k, our algorithm has a smaller threshold. In certain ranges of k, the threshold is equal, and in certain ranges, their algorithm beats ours. But let me state here also that there is another spectral algorithm for the case of k greater than omega root n, which is also given by the same paper, which matches our threshold. So, so in terms of the approximation factor, our algorithm does not do anything new, but recall that this was a simpler case only for the V minus S is a random graph. So this was a simpler case which we were studying, and we also study the two semi-random models. So ours is a sort of like a unified algorithm which solves all these problems at once. So there has been a lot of work in these so-called planted models, where you plant something in a random graph or some special structure in a special graph, and now you want to recover it. So a very brief survey of it is the following. This is studied in the work of Hayek et al., who gave SDP-based algorithms for the stochastic block model. Ames and all, they also study this problem based on non-convex, like convex but non-HDB based relaxations. McSherry et al., they consider some spectral algorithms. So lot of work on these problems. See our paper for a full discussion on these works. So let me come to the proof overview. How do we actually recover S in this random graph? So our algorithm is based on rounding a semi-definite program. So we consider some SDP relaxation, and we'll round the uh, values from that. So the idea is to convert this discrete problem into so-called geometry problem. So um, the idea is to convert this problem from a discrete to a geometry problem in, say, a much higher dimension, and work with that. So this is our SDP. The exact SDP is not important, but the point is these constraints do. There are two important points. There are which are important. Uh, One is that there is a vector corresponding to each vertex in dimension n, and these are essentially nothing but some constraints added to select k vertices. So the constraints help us in selecting k vertices, and the objective is to maximize, say, the average degree, or the average degree of the vertices or the subgraph on k vertices. So uh, but you can just think of it as like uh, maximize summation of aij vi dot vj, and this can be further decomposed into like three parts corresponding to the three different subgraphs which we have in our problem. And we know that since this is a maximization optimization problem, and uh, this is a relaxation, so this will be greater than equal to the integral objective, which is kd. So just think of it as like there's some SDP which maps our vertices to vectors, and the objective can be decomposed into three parts which has a lower bound. The integral solution, the ideal solution or the integral solution will be when vectors corresponding to a vertex and S are mapped to some unit vector E, and everything in V minus S is mapped to 0. So our SDP has the constraints allow only k long vectors. When I say long vector, I mean that a vector whose norm is close to 1, and when I say small, I mean its norm is close to 0. So the idea is to bound a contribution from the subgraphs from the random part of the graph. So you recall that the objective was a sum of three parts and has a lower bound. The first sum only dependent. The first sum, which is summation aij vi dot vj ij and s. This thing only depends on the vectors of s. And if we bound the second and the third term somehow, we can get some information about the first term. So let's see. Recall that the subgraphs on S cross V minus S and V minus S are random graphs. So we can use some standard tools. They have a lot of structures. So random graphs have a lot of nice properties, and this can be further used to bound these terms. A similar technique is used when GV minus S in an expander graph. So I'll mention what these tools are next. So the subgraph GS cross V minus is a random bipartite graph. So um, this particular thing has been studied in the literature. There is a paper by Mackenzie, Mehta, and Trevisan uh, in this year's SODA 2020, who use a combination of growth index inequality plus a union bound to bound such a term. We use sort of a spectral based proof, and use this thing called beginner's bound to show our result. For the GV minus S part, in both the cases of a random and expander, we use this weak duality to prove an upper bound on the contribution by constructing a feasible dual solution. So this idea has also been explored in this paper by Bhaskar et al. And like this is a popular method and you has been used like in many works. Um, so using these tools, we show that the the objective the SDP mass from coming from these two particular subgraphs is bounded. So it is big O of OPK square plus K into square root NP. So this essentially shows that the contribution just from S is large. That is, it is greater than equal to KD minus omega of PK square plus K square root NP. uh, Using a we can construct a special probability distribution, and under this distribution you show that expected value of vi dot vj, where ij sampled from an edge in S is greater than 1 minus omega of pk by d plus square root np by d. So when d is greater than like pk comma square root np, this particular error term is small, and we essentially show that this expected value of vi vj is like greater than 1 minus epsilon. So this is sort of like the very rough analysis of what we essentially do. We are successful in showing that the expected value of VIVJ and in this probability distribution is large. So then using some Markov's inequality and some standard analysis, and using some of the SGP constraints and so on, we can show that if we construct a set T which consists of the vertices such whose lengths are long. So if Vi square is greater than equal to 1 minus c into root of epsilon, then then the average degree of t is slightly it is greater than d into 1 minus some error term, and the size of t is k divided by 1 minus something. So it is slightly the average degree of t is slightly less than d, and the size is slightly more than d. But it turns out that this is not a major issue, and like you can sort of skip like fix this, where these c prime and c double prime are like some universal constants. So integral solution was this, I already showed you. And so the idea is the following. The algorithm is to solve the SDP, get the vectors corresponding to each vertex, pick long vectors like, and since the set was slightly greater than k, just prune the low degree vertices and output that. So this is sort of our solution, which brings me to the last part of my talk, the conclusion. So we studied semi-random models for the densest k-subgraph problem. Um, Algorithm was based on rounding a SGP solution, showed that the vectors corresponding to a planted set are clustered, used standard ideas from geometry to recover a part of the planted solution. The rest of the part was like you prune the graph slightly, you prune the set slightly to fix it. And these are some of the important selected references. I'm going to stop here for 10 seconds. And that's it from my side. And this concludes my talk.